We inhabit a galaxy known as the Milky Way, which contains hundreds of billions of stars. How did we arrive at this point, and what is our future? These concerns involve galaxies in every aspect. The known universe contains 200 billion galaxies, each of which is unique, immense, and dynamic. Where do galaxies come from? How do they work? What is their future, and how will they die? The Milky Way. This is the Milky Way, our galaxy, approximately 12 billion years old. The galaxy is a vast disk with enormous spiral arms and a central nucleus. It is only one of countless galaxies in the universe. Galaxies are massive assemblages of stars. First and foremost, a typical galaxy could contain 100 billion stars. They are actually stellar nurseries, the locations where stars are formed and perish. The stars in a galaxy are formed in nebulas, which are concentrations of dust and gas. Our galaxy contains billions of stars, many of which have planets and moons orbiting them. But for a very long time, we knew very little about galaxies. Edwin Hubble. A century ago, we believed that the Milky Way was the only galaxy in the universe. In 1924, astronomer Edwin Hubble changed everything. Hubble observed the universe using the most sophisticated telescope available at the time, the 100-inch Hooker on Mount Wilson near Los Angeles. Far, far away, he saw hazy masses of light in the darkness of the night sky. He realized they were not separate stars but entire star-filled cities, constellations far beyond the Milky Way. This revelation was an existential jolt for astronomers. In just a year, we went from thinking the Milky Way was the only galaxy to discovering there were billions. Hubble made one of the greatest discoveries in the history of astronomy when he realized that the universe contains a vast number of galaxies, not just one. Whirlpool Galaxy. This is the Whirlpool Galaxy, which comprises over 160 million stars and is characterized by two enormous spiral arms. Additionally, the stars of the huge elliptical galaxy M87 shine with a golden hue, as it is one of the oldest galaxies in the cosmos. And this is the Sombrero Galaxy, whose massive bright core is surrounded by a cloud of gas and dust. Sombrero Galaxy. All galaxies are very beautiful. They represent the fundamental building blocks of the cosmos. As they spin across space, they resemble enormous pinwheels. Galaxies are enormous on a grand scale. On Earth, we measure distance in miles, but in space, astronomers use light years. This is how far light can travel in a year. Size comparisons. Our galaxy's diameter is over 100,000 light years, and we are currently located 25,000 light years from its center. However, in the grand scheme of things, even this seems like a tiny dot. While the Milky Way seems enormous from Earth, when compared to other galaxies, it is relatively small. Andromeda, the galaxy closest to us, is about 200,000 light-years wide, making it twice the size of the Milky Way. M87 is the largest elliptical galaxy in our cosmic neighborhood and much larger than Andromeda. But M87 is tiny compared to the giant IC 1101, which is 6 million light-years across, the biggest galaxy ever found, 60 times the size of the Milky Way. It's common knowledge that galaxies are enormous and ubiquitous, but why is this the case? The origin of galaxies remains a key mystery in astrophysics. The Big Bang. Approximately 13.7 billion years ago, the universe began with what we refer to as the Big Bang, a period of intense heat and density. We know that there couldn't have been anything like a galaxy at that time, so galaxies must have formed later, emerging from the very early universe. For stars and galaxies to form, gravity is essential. Only 200 million years after the Big Bang, the first stars began to emerge, and as gravity caused masses to clump together, the earliest galaxies formed. Thanks to the Hubble Space Telescope, we can now see the early universe when galaxies were just beginning to form. The light we see from distant galaxies today actually left those objects millions or even billions of years ago, meaning we are observing the distant past of those galaxies. Hubble Deep Field. The Hubble Deep Field reveals a collection of fuzzy dots, quite different from the galaxies we see today. These barely visible blotches are the oldest galaxies, formed around 1 billion years after the Big Bang. Hubble's range of visibility, however, only goes so far. To travel farther back in time, we need a different kind of telescope, one too large to send into space. Such a telescope can not only identify primordial galaxies but also trace their evolution. Scientists can finally begin to answer the question, what did young galaxies look like? Galaxies have evolved from clusters of stars into the complex web of systems we see today. Young galaxies. As far as we can tell, the largest structures in the universe today originated as star clusters, evolved into galaxies, then into clusters of galaxies, and ultimately into superclusters. Early galaxies were filled with stardust, gas, and clumpy structures, whereas modern galaxies appear more organized and tidy. But when and how did chaotic clusters of stars evolve into neat spirals and pinwheels? The answer lies in gravity. Galaxies are shaped by gravity, and its effects determine their fate. At the center of most galaxies lies an unfathomably strong gravitational source, often a supermassive black hole. Spiral galaxies. How did galaxies evolve into their present forms? Did spiral galaxies always have to be spirals? The answer is almost certainly no. Young galaxies are chaotic mixes of stars, gas, and dust, like the Whirlpool Galaxy. Over billions of years, they evolve into more orderly formations. The Milky Way wasn't born from a single galaxy but from a cluster of several. It originated as a collection of disparate objects of varying sizes and shapes, which gradually merged to form the galaxy we see today. Gravity binds the components together, drawing stars closer over time until they flatten into a disk, with massive spiral arms gathering stardust and gas. This process has repeated countless times throughout the cosmos. Supermassive black holes. While visually distinct, galaxies share a common feature. They all seem to orbit a central object. For a long time, researchers wondered what could influence a galaxy's behavior, and they discovered the answer: a black hole. But not just any black hole, a supermassive black hole. The first indication of supermassive black holes came from detecting extreme amounts of radiation coming from the centers of certain galaxies. These black holes devour their surroundings, much like a giant Thanksgiving feast. The gas and stars around them become their dinner. Sometimes, these black holes consume so rapidly that they eject material into space as beams of pure energy. These beams are known as quasars, and the presence of a quasar is a sign of a supermassive black hole at the galaxy center. The Milky Way. But what about the Milky Way? There's no quasar here. Does that mean there's no supermassive black hole? Observing the motion of stars is the key to finding the supermassive black hole in the heart of our Milky Way. Just like planets orbit the sun, stars move due to gravity. Discovering the supermassive black hole. What we found at the center of our galaxy is a bizarre and violent environment. Everything is more extreme, and things move very quickly. Stars pass by each other at incredibly high speeds, unlike any other place in the universe. Photographs of stars in orbit revealed something remarkable. They had to be traveling at 1 million miles per hour or more. Only a gigantic black hole could have enough energy to toss massive stars around like that. This curvature of space provided conclusive evidence of a supermassive black hole at the heart of our galaxy, driving the orbits of these stars. A massive black hole, 15 million miles wide, sits at the center of the Milky Way. Is Earth in danger? Is there any danger to Earth? No, we are in absolutely no danger of being sucked into our supermassive black hole. It's simply too far away. In reality, the distance between Earth and the supermassive black hole at the center of the Milky Way is 25,000 light-years, which is trillions of miles. For now, Earth is safe. While supermassive black holes generate enormous gravitational forces, they are not strong enough to hold entire galaxies together. Dark matter. In fact, physics dictates that galaxies should be accelerating away from each other. So, what's stopping them? There is something even stronger than a gigantic black hole at play: dark matter. Dark matter is invisible and difficult to detect, but it's everywhere. Supermassive black holes discovered by astronomers are found at the centers of galaxies and account for the rapid movement of nearby stars, but they are not strong enough to hold all the stars in a vast galaxy together. The discovery of dark matter. So, what does hold galaxies together? It was a mystery until a maverick scientist, Fritz Zwicky, a Swiss astronomer, proposed in the 1930s that something unknown was at work. Zwicky reasoned that galaxies weren't producing enough gravity to keep from flying apart. The force of gravity as we understood it was insufficient. He hypothesized the existence of something that had never been discovered or even considered before, and he called it dark matter. Zwicky was decades ahead of his time, which is why he clashed with the astronomical community. Dark matter's role. Zwicky's idea was brilliant, and he was right. It's possible that individual galaxies are held together by this mysterious substance he dubbed dark matter. Galaxies rely on dark matter as a kind of protective framework that keeps them from collapsing or drifting apart. Now, scientists believe that dark matter does more than just hold galaxies together. It may have also triggered their formation and evolution. The nature of dark matter. Scientists believe that after the Big Bang, dark matter began to cluster, and these clumps of dark matter evolved into the nuclei of galaxies. However, the true nature of dark matter remains a mystery to physicists. Strange things happen with dark matter because we don't know what it is. It's clearly not made of the same substances as humans. You can't push against it, and you can't feel it, but it is likely everywhere. It's a ghost-like material that would pass right through you as if you didn't exist at all. Although our understanding of dark matter is limited, it seems to be abundant throughout the cosmos. There must be at least 6 times more dark matter than regular matter, the kind humans are made of. The way the cosmos functions depends on dark matter. Observations of its effects on light have recently led to its indirect detection in deep space through a process called gravitational lensing. Dark matter bends light due to its gravitational pull. As light from a distant galaxy travels toward us, it gets bent around a massive clump of dark matter, revealing its presence. The importance of dark matter. Now more than ever, the importance of dark matter in the cosmos is undeniable. It's what forms galaxies and prevents them from collapsing, even though it's invisible and undetectable. Dark matter essentially rules the cosmos. While galaxies may seem isolated, separated by trillions of miles, they actually exist in groups called clusters, which are further linked together into superclusters containing tens of thousands of galaxies. The Milky Way's place in the cosmos. Our Milky Way belongs to a smaller group of around 30 galaxies, with the Milky Way and Andromeda being the largest members. Further observations show that our galaxy is part of the Virgo supercluster. Researchers are mapping galaxy clusters and superclusters to better understand the cosmos. Galaxies, these massive star empires, come in different shapes, from giant spheres to intricate spirals, and they are constantly evolving. Though it may seem like our galaxy hasn't changed for eons, the Milky Way is a dynamic galaxy, evolving over cosmic timescales. Galaxy collisions. Galaxies don't just evolve, they also move, and sometimes they collide. When galaxies collide, they merge over millions of years. This kind of collision is common in the cosmos, and our own Milky Way is no exception. We are on a collision course with the Andromeda Galaxy, and this spells doom for the Milky Way. In about 5 to 6 billion years, at a speed of 250,000 miles per hour, the Milky Way will collide with Andromeda. As they approach each other, the galaxies will become increasingly disturbed, releasing clouds of gas and dust. Stars will be ripped from their orbits and flung into space. This cosmic collision will ultimately lead to the merging of the two galaxies, forming a new galaxy, Mulcometa, marking the end of the Milky Way as we know it. The end of planet Earth. There's no escaping the eventual fate of the Milky Way. What will this mean for Earth? When the galaxies collide, Earth may be thrown into the vastness of space or end up within the new galaxy's structure. Stars and planets will be thrown in all directions, and this may spell the end of planet Earth. Galactic collisions will continue across the universe, but this age of galactic cannibalism will eventually give way to an even more destructive force in the universe, dark energy. Dark energy. Dark energy, unlike dark matter, pushes galaxies apart rather than pulling them together. It is a newly discovered force and much more mysterious than dark matter. We don't know what it is made of, why it exists, or how it works, but it dominates the universe. Dark energy causes galaxies to move away from each other, and it's as though space itself contains tiny springs that push everything apart. The end of the universe. In the far future, scientists predict that dark energy will ultimately overpower dark matter in the cosmos. This will cause galaxies to drift apart, and eventually, dark energy will accelerate the expansion of the universe, forcing galaxies to recede so far from one another that they will disappear from view, traveling faster than the speed of light. The remaining cosmos will fade from sight over trillions of years. Galaxies will be left alone in the void. However, this won't happen for an extremely long time. Right now, the cosmos is thriving, and galaxies are creating favorable conditions for life to exist. Without galaxies, neither you nor I would be here, perhaps life itself wouldn't exist. This is fortunate for us because the only reason life has evolved on Earth is that our small solar system was formed in the right region of the galaxy. If we were any closer to the center, we wouldn't be here. Life near the center of a galaxy could be extremely hazardous. In fact, the proximity of our solar system to the core of the galaxy would make it so radioactive that life, in any form, would be impossible to sustain. But being too far from the center would be just as bad, as there aren't as many stars out there, and we might not exist at all. In a way, we are in the Goldilocks zone of the galaxy, not too close, not too far, but just right. There may be millions of stars in the cosmic Goldilocks zone, where conditions are just suitable for life. Moreover, if our galaxy can support life, then other galaxies should be able to as well. The cosmos is vast, and the truly amazing part is that we continue to learn new things about it. Every time we think we have solved a problem, we discover that it's just part of an even larger mystery. That is incredible. Our Milky Way galaxy and beyond. Our Milky Way galaxy, and galaxies beyond it, are full of mysteries and unanswered questions. Who could have predicted 20 years ago that we would discover the black hole at the center of our galaxy? Or that the astronomical community would embrace the existence of dark matter and dark energy? We should feel awe to be alive at this particular moment in cosmic history, on this particular planet, in this particular galaxy, with the ability to ask questions and seek answers across the entire cosmos. Galaxies are born, they evolve, they collide, and they die. The Milky Way has been a fortunate home for intelligent life, and our fate is tied to that of every galaxy. Ultimately, our fate rests in the hands of the galaxies, as they are the ones that created us and shaped our identity. The broader universe. We used to only know about the planets that orbit our sun, but now we have learned about rocky worlds and giant gas clouds that orbit other stars. They have an incredible story to tell. The early history of these planets would have been extremely violent. Planets are formed the same way everywhere, from the dust and debris left over after stars are born. If they are all made the same way, what makes them so different? It turns out the universe is full of galaxies, gas clouds, stars, and planets. In our solar system, there are 8 planets, but now we know they are just a tiny part of the vast family of planets in the sky. This is an important moment in scientific history, as we now know for certain that other planetary systems exist out there. In our Milky Way galaxy, which contains 200 billion stars, there are likely dozens of planets orbiting many of them. NASA's Kepler mission. In 2009, NASA launched the Kepler Space Telescope on a 6-year mission to discover new planets orbiting other stars. So far, it has found over 400 planets. Some are massive spinning gas giants 5 times the size of Jupiter, while others are large rocky worlds many times bigger than Earth. Some planets have wild, erratic orbits, passing so close to their stars that they are burning up. One thing is certain, no two planets are alike, each one is unique. Our solar system. Most of the new worlds discovered by Kepler are far away and hard to study. Much of what we know about how planets work comes from the 8 planets in our solar system. Our own planets come in 2 main types: for rocky planets in the inner solar system, Mercury, Venus, Earth, and Mars, and 4 gas giants in the outer solar system, Jupiter, Saturn, Uranus, and Neptune. Each of the 8 worlds is very different from the others. When our solar system was born 4.6 billion years ago, they began to develop their own unique characteristics as the sun ignited, releasing a massive cloud of gas and dust into space. All 8 planets, including the rocky planets close to the sun and the gas giants farther away, formed from this cloud of cosmic debris. While all the planets in our solar system are made of the same materials, they developed under very different conditions. Some formed close to the sun where it was much hotter, and others formed farther away where it was much colder. Because the conditions were so different, the resulting planets were also different. At the beginning of the solar system, there was a relatively even mixture of silicates, water vapor, hydrogen, methane, and other elements. These elements in the dust cloud are like ingredients in a cake. They cook differently depending on how the ingredients are mixed and how hot the oven is. Just as you'd mix the ingredients and bake the cake, the planets formed as the materials combined and changed under varying conditions in space. Overall, a planet cooks in slightly different ways depending on how close it is to the sun. Near the sun, where it's hot, gases are burned off and water boils away, leaving behind only materials that stay solid at high temperatures, like metals and rocks. This is why only rocky planets form close to the sun. As a planet moves farther away, it cooks differently. What kind of planets form depends on the composition of the dust cloud. Some solar systems might not have any rocky planets because there weren't enough materials to create something like Earth. Instead, such systems may have more gas giants. If you want rocky planets, you need a cloud full of metals and rocks. The formation of planets. As the dust cloud cools, materials with high boiling points start to condense into solids. These tiny mineral grains are the beginnings of new rocky worlds. Over time, dust particles collide and stick together, forming larger and larger grains. This process is called accretion. Small dust grains become rocks, rocks slam into each other to form boulders, and boulders smash together to create larger boulders. Eventually, a growing planet becomes large enough that its gravitational pull starts drawing in other materials, instead of just colliding with them to get bigger. In the early solar system, there were likely around 100 young planets, but most did not survive. The asteroid Vesta, for instance, gives us a good idea of how big a rocky planet must be before it can pull itself into a spherical shape. Vesta is only 329 miles across, not quite big enough to be round. A planet needs to be at least 500 miles across to have enough gravity to crush itself into a sphere. Anything smaller remains irregularly shaped. Destruction and survival. When young planets collide, the impact generates heat, causing them to melt. Gravity then starts sorting materials, with heavier elements like metals sinking to form a dense core, while lighter materials float up to form a crust. Finally, the young planets begin to look like real planets, but they still have to survive a period of violence and destruction, a brutal time that determines which planets will live and which will die. About 4.5 billion years ago, our Sun was surrounded by about 100 young planets in a chaotic demolition derby, where planets frequently collided with each other. Most were destroyed. The early history of these planets was marked by intense violence, with collisions happening in the final stages of planetary growth. As these impacts occurred, some planetesimals grew by absorbing others, leaving a debris field in their wake. Eventually, only 4 rocky planets were left: Mercury, Venus, Earth, and Mars. Each of these rocky planets is unique due to the events of their past. Mars is a frozen wasteland, Earth has liquid water, Venus is full of volcanoes, and Mercury is small, barren, and extremely hot. Mercury's thin crust and dense composition suggest it may have once been a larger planet that suffered a massive collision, stripping away its outer layers and leaving only its dense core. Earth, too, experienced a giant impact near the end of its formation, which tore away part of its mantle. The debris from that collision gathered in orbit around Earth and eventually formed the Moon. The crust of Mars is thinner in the north than in the south, and one idea about what might have caused this is that the northern hemisphere of Mars was hit by something early in the planet's history, which blew off much of its crust. That crust then started to build up again in the southern hemisphere. These collisions had 2 effects: they reduced the number of baby planets still around, and they added more ingredients to the survivors. If a planet collided with something rich in metals, those materials would sink into what was becoming the core. But if it collided with something light or icy, those materials would tend to float and become part of the crust. Close to the Sun, 4 rocky planets were almost fully formed. They had a solid core of hot iron, surrounded by a layer of liquid iron and a shell of molten rock, with a crust on the surface. Although these planets were made from the same basic materials, each of them turned out differently, with different sizes and very different fates. Space may look empty, but it's not. It's full of particles blown out of the Sun. The Sun creates strong magnetic fields that rise in giant loops above its surface. When these loops collide, they release a storm of extremely hot, charged particles into space, known as the solar wind. Astronauts can even sense it in space, but only when they close their eyes. When you close your eyes, sometimes you see a little flash, which is caused by an energetic particle passing through your head and interacting with the fluid in your eyes. These flashes happen every few minutes. The solar wind could be deadly to astronauts if they were exposed to enough of it. During the Apollo program, a solar explosion occurred between 2 moon missions that would have killed the astronauts if they had been in space at that time. Radiation in space is a major concern, but here on Earth, we are protected from the solar wind by an invisible magnetic field that comes from Earth's core. You can create magnetic fields through motion by converting kinetic energy into magnetic energy, and the same thing happens deep inside the Earth. As the Earth spins, the hot liquid metal flows around the solid core, generating a magnetic field that emerges from the poles. This field prevents the solar wind from entering the planet's atmosphere. If a planet has a magnetic field, it will divert the solar wind around it, protecting its atmosphere and everything on the surface. Occasionally, large solar storms can disturb Earth's magnetic field, creating dazzling light displays called auroras near the poles. Mars. Without a magnetic field, Earth's atmosphere and water would be blown away by the solar wind, leaving a dead, dry planet like Mars. Mars was formed the same way Earth was, but today it's cold, dry, and relatively inactive. So why have Mars and Earth changed so much over time? In 2004, NASA sent 2 robotic rovers, Spirit and Opportunity, to Mars to explore its surface. They confirmed that Mars is a dry, hazardous desert with only about 1% of Earth's atmosphere. However, they also found signs that water once existed on Mars. Mars wasn't always a barren, arid place. There is strong evidence that water once existed below the surface, rose to the surface, and then evaporated. In some areas, we can even see ripples in the sand, which are formed when water flows across it. So, if Mars once had water, it likely also had a thicker atmosphere. What happened? We can see that Mars had volcanoes in the past, which suggests it had a hot interior at one time. And since Mars was made from the same materials as Earth, it would have had a hot iron core surrounded by liquid metal, likely generating a magnetic field like Earth's. The question is, where did Mars' magnetic field go? Early in Mars' history, it probably had a strong magnetic field, created in a similar way to Earth's. But Mars is smaller than Earth, which means it loses heat faster. As Mars cooled, its liquid core solidified. When the core freezes completely, convection stops, and the magnetic field disappears. Without a magnetic shield, the solar wind stripped away Mars' atmosphere, causing its water to evaporate and turning the planet into the cold, empty place we see today. The outer planets. The rocky planets, Mars, Earth, Venus, and Mercury, all formed within 150 million miles of the Sun. But 4 times farther away, the Sun created a very different kind of planet, gas giants. These massive planets have no solid surfaces at all. So far, astronomers have discovered over 400 planets in distant solar systems, and almost all of them are giant gas planets. Our solar system has 4 gas giants: Jupiter, Saturn, Uranus, and Neptune. These planets have thick, soupy atmospheres filled with hydrogen, helium, and methane. Why are the outer planets made of gas while the inner planets are rocky? It's because it's much colder out here, 500 million miles from the Sun. At the start of the solar system, there was some dust, but mostly gas and water frozen into ice grains. It was cold enough to make solid snow where the large planets began to form. We think ice snowflakes were able to stick together to form the cores of the giant planets. This could explain why these planets grew so large. There was so much ice and gas. Their cores grew to be about 10 times the size of Earth. These large cores generated a lot of gravity, pulling in gas from around them and forming thick, soupy atmospheres that extend tens of thousands of miles deep. The more gravity they had, the bigger they became. More dust and debris were attracted to these planets, and this is how their moons formed. Jupiter and Saturn each have more than 60 moons. The gas planets have another unique feature: rings. Saturn is famous for its beautiful rings, but Jupiter, Uranus, and Neptune also have rings, though they are faint and hard to detect. All 4 gas giants have rings, but Saturn's are the most prominent. From a distance, Saturn's rings look like a single flat disk, but in reality, they are made of thousands of small rings, each only a few miles wide. When the Cassini probe flew by, it discovered that billions of pieces of ice and space debris were moving inside the rings at speeds of up to 50,000 miles per hour. These ice and rock particles frequently collide. Some turn into small moons, while others break apart, but they never grow larger because Saturn's immense gravity pulls them apart. Scientists are beginning to understand how the rings formed. One idea is that a comet hit one of Saturn's moons, knocking it out of orbit and closer to the planet. Saturn's gravity tore the moon apart, and its remains formed the rings that now circle the planet. The real mysteries of the gas giants lie deep within, tens of thousands of miles below the clouds. Here, extreme conditions defy the natural laws we are familiar with. Most of the new planets we find orbiting distant stars are massive gas giants, so large that they make Jupiter look small in comparison. But nobody knows exactly what happens inside gas giants, whether they are in our solar system or far away. We do know that Jupiter's thick atmosphere extends 40,000 miles deep, with bands of gas that create powerful storms on its surface. However, what happens deep below these storms remains unknown. NASA sent the Galileo spacecraft on a 14-year mission to Jupiter to learn more. On December 7, 1995, Galileo sent a probe into Jupiter's atmosphere, entering at a speed of 160,000 miles per hour. As it fell through the thick air, parachutes slowed it down. The probe detected lightning in the clouds and winds of 450 miles per hour. For 58 minutes, the probe transmitted data back to Earth. What happened to the Galileo probe? It didn't hit anything, it just kept falling into Jupiter's dense atmosphere, and the pressure kept rising. The probe measured pressures 23 times higher than on Earth, and temperatures over 300 degrees higher. In the deep atmosphere of a gas giant, you can be crushed by the immense weight of the material above, even though there is no solid surface. The probe only went down 124 miles before it was crushed, but it gave scientists a glimpse into Jupiter's interior. Yet the dark heart of the planet remains a mystery. Like some rocky planets, the gas giants also have magnetic fields. Jupiter's magnetic field is 20,000 times stronger than Earth's and is so large that it extends all the way to Saturn, which is over 400 million miles away. Just like Earth, Jupiter's magnetic field protects its atmosphere from the solar wind. Jupiter's magnetic field also affects its moons, especially Io, a volcanic moon that orbits just 217,000 miles from the planet. Every second, Io's volcanoes release a ton of gas and dust into space. Jupiter's magnetic field makes this even more intense, creating powerful radiation belts and making the region around the planet extremely active. In fact, if you point a radio antenna at Jupiter, you can hear the interaction between the planet and its magnetic field. Jupiter and Saturn can produce auroras without the solar wind, thanks to their magnetic fields. These auroras show that gas planets can have magnetic fields, but how do these fields form? On Earth, they are generated by hot, spinning liquid metal around a solid iron core. But gas planets don't have solid iron cores, they formed around frozen cores of dust and ice. We don't really know what's happening inside them. It's possible that Jupiter has a solid core at its center, or it could still be liquid. We might never know. No probe could travel the 44,000 miles to the planet's center to investigate. Galileo was destroyed before it could reach the core. Gravity and heat shape how planets evolve, from their inner cores to their outer atmospheres. They are the major forces in planet building, but there is one more ingredient that plays a crucial role: water. Planets may seem unchanging, but they are always evolving. One planet in our solar system lost its atmosphere and turned into a desert. Another planet got too hot and became a planet from hell. Planet Earth has also changed, and it was water that changed everything. When you look at Earth from space, you can see a lot of water. We are, after all, the blue planet. That must mean Earth is very wet, right? At first glance, our world seems to have a lot of water, since 3/4 of the surface is covered by oceans. But that's not true. Only 0.06% of Earth's mass is water. Some of it is on the surface in the form of oceans, and some is trapped in the planet's minerals, but Earth is actually a relatively dry rock. All the inner rocky planets formed close to the Sun, so they started off dry. Any water they might have had either evaporated or was blown away by impacts. The massive collisions that formed Earth were so energetic that, if there had been water here, it would have evaporated and left the planet. Water on Earth. So where did all the water on Earth come from? It's here now, but when you look at Jupiter, Saturn, Uranus, and Neptune, you can see that they have a lot of water locked up inside them. Even more dramatically, their moons have vast amounts of water. At least half of the moons of Jupiter, Saturn, Uranus, and Neptune contain a lot of water. So how did some of that water end up on Earth? The answer is almost certainly that asteroids and comets, which were far enough from the Sun to retain their water, brought it here. Millions of these water-rich asteroids and comets flew into the inner solar system, and some of them crashed into Earth. Over time, Earth gained the water that was once inside these asteroids. This is the water that now covers most of the planet. Without surface water, life would not have been possible. But what if there was too much water? The oceans would be much deeper, covering the continents and even Mount Everest. It's likely that the precise amount of water Earth has is what allowed us, Homo sapiens, to evolve into a technological species. About 4 billion years ago, a blizzard of comets and asteroids brought just the right amount of water to Earth, shaping the world we know today. It's possible that the same process is happening somewhere else in the universe right now. There's a lot of water out there, that much is certain. Hydrogen is the most common atom in the universe, and oxygen is one of the next most common. H2O is a very popular molecule, which is exactly what's happening in our universe. So water is everywhere in the universe, and we're also finding planets, but we haven't yet found a planet where water is liquid. More than 400 new planets have been discovered by scientists, but none of them look like our world. What we haven't yet found is a planet around another star that has the same size, mass, and chemical makeup as Earth. Finding such a planet remains the ultimate goal for humanity, to discover another place that reminds us of home. But we will keep looking. We know that our galaxy alone has around 200 billion stars, and up to 40 billion of them could have their own planets. We are entering what will be called the golden age of planetary exploration. In the future, we will begin to truly understand how different things are out there. I believe this will be a very exciting time. The laws of physics and chemistry tell us how planets form, and many scientists think it's only a matter of time before we find another planet like Earth, one that formed from the same materials, in the right place, with the right amount of water. One thing is certain, there are billions of planets out there waiting to be discovered. Volcanoes. Our solar system is a harsh environment. Volcanoes are destructive everywhere, from the ice volcanoes on Saturn's moon Enceladus to the vast lava fields on Jupiter's moon Io, and even here on Earth. It's true that we wouldn't be here if it weren't for volcanoes. They influence and change our climate. Volcanoes are both creators and destroyers of life. Modern spacecraft and observatories have discovered volcanoes on planets we once believed to be dead. The discovery of volcanoes on an object smaller than the moon was a major surprise. If there are volcanoes on other worlds, could there also be life? Volcanoes are among the most powerful natural occurrences on Earth. They create new land and destroy the old. They emit gases that alter the atmosphere we breathe. Deep in our oceans, volcanic heat fuels strange new forms of life. Volcanoes help sustain life on Earth, and now we look for signs of life on other planets. We know that life requires water, and we understand that it requires energy. This is where volcanoes come in, as they generate tremendous quantities of energy. If we find volcanoes on other planets, we may discover life. The search begins with our closest neighbor, Venus, a planet that closely resembles our own. Venus. Venus and Earth have similar masses. 3 billion years ago, Earth and Venus were very similar, with new land, new oceans, and an atmosphere conducive to life. However, something went wrong on Venus. Its history diverged drastically from that of Earth. A long time ago, Venus took a definite turn to the dark side. Venus is Hell, our malevolent twin planet. Today, the surface of Venus is like a furnace, with temperatures reaching 900 degrees Fahrenheit, hot enough to melt some metals. There's no chance of survival. Venus is a greenhouse world, its atmosphere containing a high concentration of carbon dioxide, which traps solar heat like a blanket. Actual images of Venus's surface reveal a barren, scorched wasteland, destroyed by its dense carbon dioxide atmosphere. The carbon dioxide was produced by volcanoes. Spacecraft in orbit provided the first clues. Radar pierced Venus's thick clouds and revealed volcanic formations all over the planet. These formations resemble Earth's shield volcanoes, which are round and flat. Shield volcanoes get their name from their shape, as they slowly ooze lava for thousands of years. When we were able to map Venus's entire surface using cloud-penetrating radar, we began to study its landforms and discovered many similarities to Earth. In particular, we observed enormous shield volcanoes that looked like those in Hawaii. The radar images of Venus's volcanoes were identical to Hawaii's shield volcanoes. In the past, Venus was home to volcanoes. When we saw images of Venus for the first time, we discovered a volcanic surface covered with craters. Carbon dioxide. There are at least 1,000 large volcanoes on Venus and possibly tens or hundreds of thousands of smaller ones. Lava plains cover 3/4 of Venus's surface, evidence of an ancient catastrophe. Venus might have once been a home for life, but instead, it was consumed by flames. Venus's volcanoes release trillions of tons of carbon dioxide into the planet's atmosphere, causing the temperature to skyrocket and the oceans to evaporate. On Earth, carbon dioxide can be absorbed by rocks and oceans, but on Venus, there is no water, and the temperatures are so high that carbon dioxide cannot combine with minerals. The volcanoes expelled carbon dioxide into the atmosphere eons ago, and over time, fewer and fewer ways existed to remove it. The volcanoes effectively sterilized the entire planet. If Venus ever supported life, it was long gone. Earth is the only known planet with life, but that may change. Another potential candidate is the gas giant Jupiter, with its moons thought to be frozen and lifeless. However, a mystery arises as a cloud hovers over a cold and barren world. Upon closer inspection, it was found that volcanoes on Venus transformed a planet similar to Earth into a hyperheated inferno. Volcanoes on a planet similar to Earth were not surprising, but the discovery of volcanoes on the Moon was astonishing. In March 1979, the Voyager 1 spacecraft provided us with our first close-up look at Jupiter's tiny moon, Io, which we once believed to be frozen and lifeless. During this observation, an arc appeared next to the moon, almost as though there was a second moon behind it. We puzzled over what this could be, because everyone believed Io to be lifeless, dull, and unremarkable, until we realized that it was a volcanic eruption. We discovered that the entire region is covered in volcanoes and geologically highly active. There are continuous volcanic eruptions, and the material ejected is primarily sulfur, which heats up and changes color as its temperature shifts. Depending on the temperature, sulfur may appear red, orange, yellow, or even black. Because of this, the images of Io's surface resemble a pizza, dotted with cheese and olives, where the small black spots represent volcanic activity. Contrary to earlier beliefs, Io is not dead, it is alive and constantly changing, with over 400 active volcanoes. The largest, Pele, erupts from a massive lava lake that reaches nearly 400 kilometers into space. If we could stand on the edge of this lake, the sight of the plume shooting into space would be incredible. These eruptions are so massive because Io is so small, with little gravity and no atmosphere to hold back the lava. These enormous eruptions make Earth's volcanoes seem like mere fireworks by comparison. How can such a small moon be so volcanically active? The answer lies with Jupiter. Similar to how Earth's moon creates tides in our oceans, Jupiter raises rock tides on Io. Io's orbit around Jupiter isn't circular, it's sometimes closer, sometimes farther away. Jupiter's gravitational pull stretches and compresses Io during each 2-day orbit, causing the ground to rise and fall by nearly 300 feet. This constant distortion generates heat and pressure, causing lava to erupt through weak spots in the crust. As a result, Io's volcanism is planet-wide, unlike Earth where volcanic activity is localized along tectonic plates. On Io, the entire moon is a volcanic hotspot, making it the most volcanically active body in the solar system, thanks to the immense power of gravity. Volcanic activity on Io has taught us something new. Internal energy sources can drive volcanism in a different way from Earth. Io is a world of lava, intensely hot and violent, making it hard to imagine life surviving there. Although we've seen volcanic eruptions on many planets and moons, so far Earth is the only world where volcanism is connected to life, or so we thought. This is Europa, another moon of Jupiter, orbiting nearly 500 million miles from the Sun. Europa is a 2,000-mile wide sphere of ice. From afar, its surface looks polished, but up close, it's different. Europa is battered by Jupiter's gravity, just like Io, causing the surface to rise, bend, and form ridges and deep fissures. When we first got close-up images of Europa, its surface seemed familiar, resembling Arctic ice flows on Earth, and it turns out they're quite similar. Beneath Europa's several-mile-thick icy crust lies a global liquid ocean. Magnetic measurements indicate this ocean is an astounding 60 miles deep. The gravitational pull from Jupiter heats the rocky interior, melting the ice above. As the core is stretched and heated by tidal forces, it's not far-fetched to believe there's a boundary between the hot core and the liquid water ocean. On Earth, underwater volcanic eruptions are teeming with life. The same may hold true for Europa, where in the dark, under immense pressure, up to 2,000 Earth atmospheres, it's a harsh environment, but perhaps a cradle for life. If life exists in extreme conditions on Earth, why not on Europa? There are energy sources like volcanic activity, a universal solvent in liquid water, and a complex hydrocarbon chemistry, all essential ingredients for life. Though life would be difficult, it wouldn't be impossible on Europa. Life thrives in every extreme environment on Earth, from intense heat to crushing pressure and total darkness. Life on Europa may resemble life on Earth in unexpected ways. If life exists beneath Europa's icy surface, it would likely be aquatic but without eyes, since there's no light. These organisms might live off the energy from volcanic activity and rely on sonar to navigate their surroundings. Volcanoes on Europa could be the birthplace of new life. It's even possible that Europa is typical of life-bearing worlds, and Earth might be the exception. Europa could serve as a model for billions of moons across the universe with liquid oceans. This suddenly expands our horizons by several billion times. By examining Jupiter's moons, we see that our solar system alone is home to over 170 moons. Multiply that by the number of moons in the universe, and the potential habitats for life become immense. The essential ingredients for life, liquid water and a source of energy, may be provided by volcanoes, which are found throughout the universe. This brings us to Saturn, which is twice as far from the Sun as Jupiter, and yet also has volcanic moons that could support life. Saturn is one of the most unusual planets in our solar system, with a 600,000-mile wide ring system and an incredible 62 moons. One of these moons holds a secret, Enceladus. Enceladus is one of Saturn's smaller and more distant moons, and it's long been known to be covered in ice because of its bright, reflective surface. However, when the Cassini spacecraft visited Saturn, it made a remarkable discovery, not on the planet itself, but on Enceladus. Cassini revealed a massive plume erupting from Enceladus, backlit by the Sun, offering conclusive evidence of volcanic activity. Cassini's sensors zoomed in on the Moon's south pole and captured giant craters scarring its surface. At Enceladus' south pole, there are enormous fissures that open and close as the Moon orbits Saturn, due to tidal forces. These fissures are hundreds of kilometers long, and when they open, a massive crevasse moves at about 100 miles per hour along its length. It's an awe-inspiring sight. The gravitational forces pulling the surface apart create the heat needed to melt the ice, forming oceans beneath the surface. The water under Enceladus' surface is ideal for life. It's at the perfect temperature, and the liquid water would be just like seawater on Earth. The chemistry of the water observed in the plumes erupting from the fissure suggests it contains salt and organic matter. We've identified a location in the solar system where there's a strong possibility of life existing right now. Cassini detected complex carbon molecules in the ice particles erupting from Enceladus, and in combination with liquid water, this suggests that life could exist deep within this mysterious moon. Enceladus might not be the only moon of Saturn that harbors life. Titan, another moon of Saturn, may also hold the key to life. Titan is one of the largest moons in our solar system and the only one with a thick atmosphere. It's a frozen world where ice is as hard as rock and lakes are filled with liquid methane. Despite these harsh conditions, there may also be evidence of volcanoes on Titan, hinting at the possibility of extraterrestrial life. Volcanoes are among the most destructive forces in the universe, as seen in the fiery eruptions on Io and the ice and nitrogen explosions on Triton. Even on Saturn's mysterious moon Titan, destruction could pave the way for life. Titan, with a diameter of 3,000 miles, is larger than Mercury and has the thickest atmosphere of any moon in our solar system. It experiences weather patterns, including cyclones, winds, rain, and even lakes. However, the temperature is so low that liquid methane takes the place of water, and it is filled with compounds essential for life. Titan has proven to be one of the most fascinating locations in the solar system. It's an active world, the only moon with a dense atmosphere, similar to Earth's due to the presence of nitrogen. In Titan's upper atmosphere, methane gas reacts with sunlight to produce organic compounds that are necessary for life. But if sunlight is consistently converting methane into organic compounds, why hasn't the methane run out? Methane is abundant in the atmosphere, yet we know that it's quickly broken down by sunlight, so it shouldn't be there. There must be a source of methane. Something on Titan is emitting methane continuously. Cassini has detected what seems to be a crater, and infrared cameras reveal that it is surrounded by various types of materials. Scientists believe the green areas may be volcanic plains, possibly created by lava ejected from Titan's interior. On Titan, the boiling liquids emitted by volcanoes could be ammonia or water. Methane and ethane are also expelled from Titan's volcanoes, likely contributing to the moon's thick cloud cover and orange atmosphere. This atmosphere probably originated from the outgassing of Titan's volcanoes. Even on a rigid body like Titan, volcanoes require heat, and on Titan, there are two main sources of heat. Radioactive substances warm the interior, and Saturn's immense gravity pulls on the moon, similar to Enceladus. These two forces generate enough heat to turn ice into water and liquid methane into gas. Could these volcanoes on Titan provide the conditions needed for life to exist? The chemical reactions required for life as we know it need an atmosphere, a solid surface, liquid water, and heat. Volcanoes could offer all of these on Titan. If life exists on Titan, it would be truly alien. It would breathe hydrogen instead of oxygen and might swim through methane reservoirs at temperatures 300 degrees below zero. There could even be oceans of ethane and possibly tidal pools, along with volcanic and hydrothermal activity. Volcanic heat might produce enough energy to support life on Titan, though this is speculation. It cannot be ruled out. However, we may not need to travel that far to find signs of life. We may discover life on Mars, a volcanism-rich planet much closer to home. Volcanoes are common throughout the solar system. On planets like Io, Titan, and Triton, they are volatile and violent. We once believed Earth was the only planet with both volcanoes and life, but now we find volcanoes everywhere. Still, alien life has yet to be discovered. Volcanoes exemplify the sheer power of creation and destruction, both of which are intertwined. It's literally true that without volcanoes, we wouldn't exist. Volcanic cauldrons are the birthplaces of life. Volcanoes shape new landscapes, seed the atmosphere with complex chemicals, and replace the old with the new. If volcanoes are connected to the processes of life, then where is life on other planets? Perhaps the key to this question lies in ancient times, when the solar system was young, on a planet similar to our own. That planet is Mars. 3 billion years ago, Mars was volcanically active, and the greatest volcano in the solar system still stands today. The cliffs leading up to it are over 6 miles high, dwarfing even Mount Everest. This is the formidable Olympus Mons, covering an area the size of Arizona. Its crater alone is 53 miles wide. A structure of this size takes millions of years to form, a time span Earth's volcanoes never experience. Earth's crust is constantly shifting due to tectonic activity. Deep within the Earth, a stationary hotspot forces magma to the surface, creating a new volcanic island. As the surface moves, the new island drifts away from the hotspot and is replaced by another. Mars is different. The crust on Mars is locked solid, with no tectonic activity, the crust is one big solid plate. So if there's a hot spot, it just sits there and builds, creating larger and larger volcanoes. That's why Olympus Mons is so enormous. Today, Olympus Mons is an icy remnant of a distant, warmer era. Olympus, an extinct volcano on a fading planet, is now a veritable colossus due to Mars' diminished atmosphere. However, the ancient volcanic terrain of Mars could one day support life. The evidence is readily available on Earth. Volcanoes in Hawaii have formed enigmatic tunnels known as lava tubes, which are created when rivers of molten rock rush into the ocean. Lava tubes form when there is an underground river of basaltic lava, magma, and molten rock at 2000 degrees Fahrenheit. Imagine it as an icy river with a crust of ice forming on the surface, except, in this case, the crust is solid rock, and the river continues to flow beneath, creating a cave or lava conduit. Recent images suggest that Mars volcanoes may have also created lava tubes. Any rocky planet with basaltic volcanism will likely contain lava pipelines. After possibly millions of years of inactivity, these lava tunnels could revive life on the red planet. This life could be our own. Radiation is one of the challenges future humans will face when attempting to live on Mars, especially during solar storms. Incoming cosmic rays can be lethal. The tunnels and caverns of Mars' extinct volcanoes could one day serve as ideal shelters, retaining air and shielding us from harmful radiation. A long-dead volcano could help fill a world with new light. Volcanoes are capable of both destruction and creation. On a night in early September 1859, people all over America could see the aurora. It was blood red and so bright that miners in the Rockies, emerging from their tunnels, thought the sun was rising. It was so bright that at midnight, one could even read a newspaper by its light. This phenomenon was observed all over the world. No one knew why it had happened, but earlier that same day, an astronomer had observed something on the sun's surface that he described as a white light flare. Back then, the flare and the aurora seemed unrelated, but we now know that the spectacular aurora was caused by that flare, which was a coronal mass ejection. If such a violent event were to happen again, it could destroy our modern technological world. The sun is the most familiar object in the sky. It provides all life on Earth with heat and light. It's so massive that it's hard to imagine, making up 99% of the mass of the solar system. This nearly perfect sphere has a diameter of 1.4 million kilometers and has been burning hydrogen and helium for the last 5 billion years. Yet, from an astronomical perspective, it's nothing special, a G-type main sequence star, also known as a yellow dwarf. But appearances don't tell the whole story. Solar flares and explosions of plasma particles and radiation from its surface travel far into space in a process we call the solar wind. Solar storms, on the other hand, are very violent eruptions, and a coronal mass ejection is the most dangerous because it has the potential to bring our high-tech society to its knees. Today, we'll learn how bad a coronal mass ejection could be and what astronomers are doing to monitor our star in hopes of predicting when such an event might occur. Let's step back in time to 1859. In Victorian Britain, it was acceptable for a gentleman to take an interest in solar astronomy, and one man who did so was Richard Christopher Carrington. We don't know what he looked like because no known portraits of him exist, but Carrington made several important observations. He discovered that different latitudes of the sun rotate at slightly different speeds, indicating that the sun is not a solid body but a fluid one. He also realized that sunspots could signal the onset of a solar storm. On Thursday, September 1, 1859, there were no clouds in the morning sky, so Carrington was doing his usual routine of observing sunspots. Using his telescope to project an image onto a screen, at 11:18 a.m., he witnessed two brilliant beads of blinding white light appear in what he described as a kind of conflagration. Stranger still, they disappeared after 5 minutes without explanation. What Carrington had observed was a coronal mass ejection, a massive magnetic explosion where a huge cloud of charged particles was hurled off the sun's surface. 18 hours later, Earth was hit by an electromagnetic storm, now referred to as the Carrington event. At the time, people marveled at the beautiful auroras visible worldwide. Although a few telegraph systems experienced power surges and malfunctions, the event didn't significantly affect daily life. Keep in mind, this was 20 years before the invention of the light bulb. That was in the past, but things would be very different if it happened today. Coronal mass ejections are common, but they vary in size and direction. The question is, what are the chances of something like the Carrington event happening again today, and how would it impact us? So, what is happening on the Sun? On the surface of the Sun, when we talk about the solar wind and space weather, we're dealing with magnetic fluid. As this fluid rotates, it twists and distorts the Sun's magnetic field. A twisted magnetic field stores energy, which can lead to eruptions known as coronal mass ejections. These explosions are massive, sending out 1 billion tons of material at 1 million miles per hour. That's why it's important to track where these eruptions are headed, because if they move toward Earth, they could disrupt the technologies we rely on. A famous event occurred in Quebec in 1989, where power systems were disrupted for several hours due to a solar storm. We've also heard about the Carrington event in the 1800s. But what would happen if it occurred today, and how would it affect us? Think about the technologies we use today: GPS satellites that help us navigate, communication satellites, weather satellites, and even financial systems like the stock market, which are all linked in some way. We also have larger power grids and much more wireless technology, but we don't know exactly how these would react. How likely is it for something like the Carrington event to happen again? We know the Sun is still capable of causing such events. In 2012, there was a solar event that, luckily, didn't head toward Earth, but it did pass over one of the spacecraft we use to monitor the solar wind. The coronal mass ejections pushed all the sensors on that spacecraft to their limits. Based on what we've learned, that event was at least as powerful as the Carrington event, if not more so. It was pure luck that a coronal mass ejections of that magnitude wasn't headed toward Earth. It's essentially a matter of chance. Sometimes we get hit, sometimes we don't. How are we doing with solar predictions? Can we forecast what the Sun will do in a week, a month, or a year? Once a coronal mass ejections is detected, we can start making predictions to figure out how large it is, how fast it's moving, and most importantly, where it's headed. This all sounds quite scary, and space weather is indeed a real concern. The UK government acknowledges this. In fact, the National Risk Register lists space weather as a risk on par with a flu pandemic. To mitigate these risks, spacecraft engineers are working to determine the most extreme space conditions so they can build satellites capable of handling them. Both NASA and the European Space Agency are preparing to send satellites closer to the Sun than ever before. In 2014, the Met Office's Space Weather Operations Center opened, and it's one of only 3 centers worldwide that can predict the Sun's effects on Earth 24/7. So far, the Sun has shown almost no sunspots, and the side facing Earth is not expected to produce any significant sunspots or coronal mass ejections. Fortunately, there's not much activity at the moment, and things aren't expected to change drastically in the near future. For now, spacecraft, satellites, and power systems should be safe for the foreseeable future. The problem is, the foreseeable future in space weather forecasting only covers a few days. We still don't know much about coronal mass ejections, such as where they're headed, how big they are, or when they might happen in the future. However, 2 new solar probes will soon get closer to the Sun than any spacecraft has ever been. The Parker Solar Probe is set to be sent into space, and its destination will take it closer to the Sun's surface than any other spacecraft has ever gone. It will fly through the source of the most energetic solar particles. The Parker Solar Probe is an exploration mission designed to measure the gas and magnetic fields near the Sun to understand why this material spreads out into the rest of the solar system. The European Space Agency's Solar Orbiter is another mission aimed at discovering how sunspots, flares, and coronal mass ejections on the Sun's surface are related to the solar wind. The success of the Solar Orbiter will be crucial to our understanding of how the Sun functions. We believe that the Sun's magnetic field is generated in a similar way to Earth's, but it is far more dynamic and constantly changing. The Sun has an 11-year sunspot cycle during which its magnetic fields move toward the poles, and its polarity reverses. Additionally, the Sun's magnetic field extends into the solar system and flows over all the planets. The Solar Orbiter will measure these magnetic fields for the first time and will also provide us with the opportunity to observe them as they move to the Sun's poles. To achieve this, the Solar Orbiter will capture images of the Sun's atmosphere and measure the number, speed, and temperature of particles moving through the space between the Sun and Earth. One of the most significant and sensitive instruments on board is the magnetometer, designed to measure the tiny magnetic fields in space that are carried by the solar wind. The Sun is ever present in our lives, providing light, warmth, and even life itself. For Richard Carrington, who was the first to record a coronal mass ejection, it was just a strange event. But now we know that these events can cause significant damage to our modern world. With new satellites and more observations, we may be able to learn more about these events and predict when the next coronal mass ejection will occur. Venus is nearly identical in size to Earth, making it one of our most similar neighbors in the solar system. With a mean radius of about 3,760 miles, it is approximately 95% the size of Earth. Its mass is about 81.5% that of Earth. This similarity in mass and size also means that Venus has a comparable density to Earth, around 5.24 grams per cubic centimeter, suggesting a similar rock-iron composition. Both Venus and Earth share a similar structure, a central iron core surrounded by a rocky mantle and a thin crust. The core of Venus, though not as well understood as Earth's, is believed to be partially liquid, much like Earth's. This iron core is estimated to be about 2,000 miles in diameter. Above the core lies Venus's mantle, composed of silicate rock that extends up to approximately 1,550 miles from the planet's center. The mantle is overlaid by a thin crust, estimated to be between 6 and 12 miles thick. One unique characteristic of Venus is its unusual rotation, which sets it apart from the other planets in our solar system. Unlike most planets, which spin on their axes in the same direction as they orbit the Sun, Venus rotates in the opposite direction. This phenomenon isn't fully understood by scientists, but some believe it may be due to a massive collision with a celestial body in the past, which altered the planet's rotational dynamics. Venus rotates extremely slowly, with a sidereal day taking 243 Earth days, the slowest rotation of any planet in the solar system. This slow rotation contributes to the planet's lack of a significant magnetic field. Another unusual aspect of Venus's rotation is that a solar day is shorter than its sidereal day due to its retrograde rotation and orbit around the Sun. A solar day on Venus is about 116.75 Earth days. The planet's year, the time it takes to orbit the Sun, is about 225 Earth days, making Venus one of the few planets where a day is longer than a year. The surface gravity on Venus is about 90% of Earth's gravity, meaning that if you were able to stand on Venus, you would feel slightly lighter than on Earth. However, the extreme atmospheric pressure and temperature would make it impossible for humans to survive without protection. Venus's surface appears to be geologically young, with relatively few craters, indicating a surface age between 300 million and 600 million years. Scientists believe Venus undergoes a cyclical process in which heat from the planet's interior causes the surface to be repaved in a global resurfacing event. There is strong evidence of widespread volcanic activity on Venus. Thousands of volcanoes dot its surface, ranging from less than a mile in diameter to over 150 miles. Venus has far more volcanoes than any other planet in our solar system. However, there is no definitive evidence that these volcanoes are still active, although recent studies suggest some may have erupted within the last few million years. Despite apparent geological activity, Venus doesn't experience significant tectonic activity like Earth. While Venus does have mountain ranges and rift valleys similar to those seen in tectonically active regions on Earth, it lacks the large, distinct tectonic plates seen on our home planet. This might be due to the planet's slow rotation, which limits the Coriolis effect necessary to drive large-scale tectonic activity. One of Venus's most distinctive and intriguing features is its atmosphere. The atmosphere is primarily composed of carbon dioxide, with most of the remaining 3.5% being nitrogen. There are also traces of other gases, such as sulfur dioxide, water vapor, carbon monoxide, argon, and helium. This composition is vastly different from Earth's nitrogen-oxygen atmosphere, making Venus's air toxic to humans and most known forms of life. The atmosphere of Venus is divided into several layers: the troposphere, extending from the surface up to about 40 miles, the mesosphere, stretching from the top of the troposphere to about 56 miles high, and the thermosphere, which reaches up to 125 miles above the planet's surface. Above this is a transitional region called the exosphere, which merges with the vacuum of space. The high concentration of carbon dioxide in Venus's atmosphere creates a strong greenhouse effect, trapping heat and making it the hottest planet in the solar system, even hotter than Mercury, which is closer to the Sun. Greenhouse gases in the atmosphere absorb heat energy radiated from the Sun, preventing it from escaping back into space. This results in surface temperatures averaging around 467 degrees Celsius, hot enough to melt lead. There is very little temperature variation between day and night or between the equator and the poles, due to the thick atmosphere's efficient heat distribution. This creates a virtually constant furnace-like temperature across the planet's surface. The atmospheric pressure on Venus is enormous, approximately 92 times greater than Earth's at sea level. This is equivalent to the pressure experienced 0.62 miles deep in Earth's oceans. A human exposed to such pressure without protection would be crushed. However, higher up in Venus's atmosphere, about 31 miles above the surface, the pressure and temperature conditions are similar to those on Earth's surface. Venus's atmosphere is perpetually cloaked in thick, opaque clouds that cover the entire planet. These clouds reflect about 75% of the sunlight that reaches Venus back into space, which is why Venus is so bright and easily visible from Earth. The winds in Venus's upper atmosphere are incredibly fast, reaching speeds up to 450 miles per hour, much faster than the strongest hurricane winds on Earth. These winds create a phenomenon known as superrotation, where the atmosphere rotates much faster than the planet's surface. Near the surface, however, winds are much slower, typically less than a few miles per hour. Venus is home to the highest mountain in the solar system, Maxwell Montes, which rises 20 kilometers above Venus's mean surface level. The planet's surface is also marked by numerous impact craters, extensive lava flows, and unique surface features like coronae, circular structures caused by the upwelling of hot material from the mantle, and arachnoids, circular structures with complex patterns of fractures. Due to Venus's slow rotation and dense atmosphere, the planet doesn't experience significant seismic activity like Earth. However, recent studies suggest that Venus may still be geologically active. Venus has been a target of interest since the dawn of space exploration. The Soviet Union's Venera and Vega missions, NASA's Pioneer Venus, and the European Space Agency's Venus Express have all contributed significantly to our understanding of the planet. The Venera program achieved many firsts, including the first human-made device to enter the atmosphere of another planet and the first successful landing on another planet. These missions provided valuable data on Venus's atmosphere and surface. More recently, NASA's Magellan orbiter mapped almost the entire surface of Venus using radar to penetrate the thick cloud cover, revealing details about Venus's surface features and geology. Despite the challenges posed by Venus's harsh conditions, scientists are keen to continue exploring the planet. NASA's planned Veritas and Da Vinci Plus missions aim to study Venus's geologic history and atmospheric conditions, providing insights into whether Venus might have once harbored liquid water or even life. Meanwhile, the European Space Agency's Envision mission will focus on understanding why Venus and Earth took such different evolutionary paths. Japan's Akatsuki mission is currently studying Venus's atmosphere and weather patterns. Venus, our neighboring planet, is an intriguing world of extremes. Its harsh environment poses significant challenges to exploration, yet its similarity to Earth in size and composition, along with hints of potential past water and geologic activity, keep our curiosity alive. As we prepare for new missions to Venus, we stand on the brink of major discoveries that could reshape our understanding of the solar system and our place in it. As a reflection on our own planet's potential future, Venus serves as both a warning and an opportunity for scientific discovery. Space has always captured humanity's collective imagination. Among the pantheon of celestial bodies that have fascinated us, Jupiter stands out as the largest planet in our solar system, with its vibrant stripes and prominent great red spot making it easily recognizable. However, there's much more to Jupiter than just its size and famous storm, and our knowledge has grown exponentially with advancements in space technology and exploration. Jupiter is a gas giant, primarily composed of hydrogen and helium. Its diameter is approximately 11 times that of Earth, and it is so large that over 13 Earths could fit inside it. Despite its size, Jupiter has the shortest day of all the planets, rotating on its axis every 9.9 hours. Jupiter's magnetic field is the strongest of any planet in the solar system, created by electrical currents driven by its fast rotation and the movement of metallic hydrogen within its outer core. Jupiter's famous bands are actually high-pressure zones characterized by lighter-colored clouds, while its darker regions are low-pressure zones. The vibrant colors we see are due to different types of clouds. Ammonia crystals create the white bands, while other chemicals produce the reddish, brownish, and yellowish hues. The Great Red Spot is a persistent high-pressure region in the atmosphere, resulting in a storm that's been ongoing for at least 300 years. At its widest point, the Great Red Spot stretches 1.3 times the diameter of Earth, though it has been shrinking in recent decades. The storm rotates counterclockwise with a period of about 6 days, and its size, speed, and color can change. The longevity of the Great Red Spot is likely due to Jupiter's rapid rotation and the lack of a solid surface, which minimizes frictional dissipation of the storm's energy. Studying the Great Red Spot helps scientists understand the atmospheric dynamics of Jupiter, a gas giant with vastly different conditions from Earth. Jupiter's 4 largest moons, Io, Europa, Ganymede, and Callisto, are known as the Galilean moons, named after Galileo Galilei, who discovered them in 1610. Each of these moons is unique. Io is the most volcanically active body in the solar system, Europa has a crust of ice and may harbor a subsurface ocean, Ganymede is the largest moon in the solar system and has its own magnetic field, and Callisto is heavily cratered and may also have an ocean beneath its surface. As of my knowledge cutoff in September 2021, Jupiter had 79 known moons, though additional moons may have been discovered since then. Jupiter also has rings, although they are much fainter and smaller than Saturn's. These rings were first discovered by NASA's Voyager 1 spacecraft in 1979, and are composed mainly of dust particles from impacts on Jupiter's small inner moons. Space exploration missions like Pioneer 10 and 11, Voyager 1 and 2, Galileo, and Juno have provided invaluable insights into Jupiter's composition, magnetic field, and moons. Juno, still active as of 2021, has contributed significantly to our understanding of Jupiter's internal structure, atmosphere, and magnetosphere. Jupiter remains a focal point of curiosity for astronomers and space enthusiasts alike. Its impressive size, complex atmospheric dynamics, numerous moons, and faint ring system make it a fascinating object of study. As we continue to explore Jupiter through telescopic observations and space missions, we unravel the secrets it holds, enriching our understanding of the cosmos. For now, we marvel at the celestial symphony Jupiter conducts, a testament to the intricate, diverse, and vast nature of our solar system.